Popular physics discussions claim that the delayed choice quantum eraser experiment allows scientists to change the past. It suggests that a choice made today can reach back in time to alter how a particle behaved years ago. We are going to step through the mechanics of this experiment to show why that claim is a misunderstanding of the math. Niels Bohr's complementarity principle provides the starting point for our quantum system. It states that a quantum particle possesses two mutually exclusive natures. It can act as a wave, or it can act as a particle, but it can never exhibit both behaviors in a single measurement. In a standard double-slit setup, an unobserved particle behaves like a wave, traveling through both slits to create a striped interference pattern. However, tracking its path changes the outcome. The wave vanishes and the particle strikes the screen, forming two distinct bands instead. Because path knowledge and wave interference are mutually exclusive, the presence of one always necessitates the absence of the other. You cannot know the route and see the stripes at the same time. To test the limits of this rule, we can add physical detectors to the slits. Detector D1 monitors the top path, and D2 monitors the bottom. Simply recording this path information forces the particle to act like a particle. The striped interference pattern washes out into a featureless clump of hits on the screen. We can erase this path information by merging the detectors into mixed states, which we will call D+ and D-. In these states, the information is combined so that we can no longer distinguish which specific slit the particle used. Erasing the path data allows the wave behavior to return. If we separate these hits by their connection to the mixed states, we see that particles linked to D+ form one interference pattern, while those linked to D- form a second, shifted pattern. The two patterns are perfectly out of sync. The peaks of the D+ pattern perfectly fill the troughs of the D- pattern. When they overlap, they create the appearance of a solid, featureless clump. The interference remains present in the combined data. It is only invisible because the two patterns overlap. The only way to resolve the stripes is to filter the hits by their connection to the D+ or D- states. Now consider the delayed choice scenario. We move our path detectors light years away, so the particle hits the screen long before the path information is even recorded. If we decide to erase the data years after the particle has landed, does that choice reach back in time to tell the particle to act like a wave? The answer lies in the mechanics of quantum entanglement. When two particles are entangled, they exist as a single system, where the state of one is tied to the state of the other, regardless of distance. The measurement at the screen, which we'll call X, and the distant path detector, Y, are a single entangled pair. The math shows that their states are correlated from the moment of the particle's birth. When the particle hits the screen at a specific coordinate, that measurement instantly locks the distant path detector into a D+ or D- state. Because the landing position on the screen is already fixed, the corresponding state of the path detector is also fixed before the experimenter ever looks at it. The experimenter isn't making a choice that changes the past. They are simply observing a state that was determined the moment the particle hit the screen. In a multi-channel setup, odd number detectors are tied to the D+ state and even number detectors to D-. When a particle lands on an odd detector, it instantly forces the distant path detector into D+, and even hit forces it into D-. The universe preserves the consistency of the timeline on its own. The path information is effectively erased by the particle's landing position, preventing any potential time travel paradoxes before they can happen. To summarize, in the path known state, we see particle behavior. In the path erased state, we filter the data to see hidden wave fringes. And in the delayed eraser, the screen strike itself determines the state of the distant path detector through entanglement. Quantum mechanics is undeniably strange, but it follows a strict internal logic that respects the forward flow of time. By looking at the math of entanglement, we see that Bohr's complementarity remains as consistent as ever.